All right, let's talk about LLMs. We've all heard the phrase autocomplete on steroids, right? But today we're going to peel back that layer and get into how these things actually work. We'll start with a definition that's really close to perfect, and then we'll refine it together to get to the core of it.
So, let me just ask you, how solid is your mental model of an LLM? For a lot of us, it's pretty good, but, the devil's in the details. The goal here is to take that almost perfect idea and just click it into place, make it truly solid. So, let's dive in.
Now have a look at this. As a starting point, this definition is fantastic. Seriously, it touches on prediction, tokens, embeddings, a geometric landscape, even the neural network. It gets you about 90% of the way there. But that last 10%, that's where the real magic is. So let's make 3 key corrections that will get our understanding from 90% all the way to 100%.
Okay, our first big correction is all about how the model actually finds information. The original definition said it tries to find a mathematical match, which kind of makes it sound like a simple search, a one-and-done lookup. But the reality is way more active than that.
So let's just get rid of this idea of finding a mathematical match. A much better way to think about it is that the input has to undergo repeated mathematical comparisons and transformations. It's not a search, it's a dynamic, evolving process. Let's break down what that actually looks like.
Think of it as this incredible cascade of events. Your input gets projected through the network's learned weights, which is really just a map of all its statistical knowledge. This kicks off millions of super-fast comparisons. Then, this thing called an attention mechanism gets to work, figuring out which parts of your input are most important. And as this signal flows through the network, layer by layer, the model's internal picture of your request gets updated and refined. It's a constant flow, not a single snapshot.
All right, on to correction number 2, and this one is a big one. The original idea hinted that the model finds the answer. But here's the thing, the answer doesn't exist anywhere in the network just waiting to be found. Instead, the model actually builds something totally new in that moment.
And that's something that it builds is what we call a contextual state. The whole point of that cascade of comparisons we just talked about is to construct this temporary internal understanding of what you just said. This state doesn't contain the answer. What it does is dramatically rig the competition for what the next word should be, making some tokens astronomically more probable than all the others. And that brings us to our third and final refinement. It's all about separating 2 totally different phases of an LLM's life. See, the initial definition kind of mushed statistics and probability together, but things get a whole lot clearer when you split apart when the model learns from when it talks.
The key is to see these as 2 distinct jobs. Training is the enormous one-time process where the model learns all the statistical patterns from its data and basically freezes that knowledge into its weights. But inference, that's what happens when we're actually talking to it. That's the live process of using that frozen structure to generate probabilities for what the next word will be. One builds the machine, the other runs it.
Okay. So with those 3 big ideas in our back pocket, the cascade of comparisons, the creation of a contextual state, and that crucial difference between training and inference, we're ready. We can now put together our final, much more precise definition of how an LLM works. But first, let's just give credit where it's due. That initial guess was solid. Prediction engine, tokens, embeddings, this whole idea of a geometric landscape and a signaling cascade, all of that is the right skeleton. We've just added the really important connective tissue to make it all work. And here it is, our refined definition. Notice those crucial upgrades, right? We now specify it's a probabilistic engine using a frozen network. And inside, it's not finding anything. It's using repeated comparisons to build a temporary contextual representation. And it's that state that shapes the probability of the next word. It's these more dynamic ideas that give us a way more accurate picture.
But let's go one step further. Can we boil all of this down to its absolute essence? After everything we've talked about, what's the one thing you really need to remember? Let's get to the final punchline.
So, if you walk away with just one thing today, let it be this. There are no facts stored in an LLM. There are no sentences just sitting there. There are only learned dispositions. These are just tendencies for the network to behave in certain ways when it sees certain patterns. And it uses those tendencies to generate the most probable next word for whatever you give it, literally building meaning on the fly.
And that leaves us with a pretty fascinating final thought, doesn't it? If this incredibly powerful new kind of intelligence doesn't know things by storing facts, but by creating meaning from patterns in the moment, well, What does that say about our own understanding of what it means to know something? Something to think about. Thanks for tuning in.